let's start liquid plus liquid solution. Before starting it, please tell me what is vapor pressure of liquid? Yes, what is vapor pressure of liquid? Vapor pressure of liquid. Okay, to make you understand, let me draw a diagram. What happens, students? When you put a volatile liquid in a container, it evaporates and form vapor until an equilibrium is reached between this vapor phase and this liquid phase. Okay, and at equilibrium, the pressure exerted due to this vapor on the liquid surface is known as vapor pressure of liquid. The most important thing is that the pressure exerted by the vapor over the liquid at equilibrium is known as vapor pressure of liquid. Okay, so now you understand what is vapor pressure of liquid. Now let's take a binary solution of two volatile liquids 1 and 2. So these are the two volatile liquids. Okay, and when you put it in a container, what happens? It will evaporate and form vapors until an equilibrium is reached between this vapor phase and this liquid phase. Here you can see these blue dots. These are the vapor created due to liquid 1 that I have named as vapor 1. And these black dots, these are the vapors created due to liquid 2 and that I have named as vapor 2. Okay, so now what happens? It will evaporate until equilibrium is reached. And what happens when equilibrium is reached? At equilibrium, suppose P total is the total pressure, P1, P2, these are the partial vapor pressure of component 1 and 2, x1 and x2 are the mole fraction of component 1 and 2 in solution. Okay, so at equilibrium, the pressure exerted due to this vapor 1 is known as P1, and at equilibrium the pressure exerted due to vapor 2 is P2. Okay, and the total pressure generated due to these both vapors, vapor 1 and vapor 2, is known as P total. Okay, now what is x1 and x2? We call it as mole fraction of component 1 and 2 in solution. Suppose liquid 1 is present 2 mole in solution. Here you can see So this is the solution. Okay. Suppose liquid 1 is present 2 mole, and suppose liquid 2 is present 4 mole. Okay, in this solution. Now what is x1? X1 is mole fraction of component 1 in solution. So mole fraction of component 1 in solution, it is present in 2 mole. So 2 mole divided by total moles, 4 plus 2 mole, that equals to 2 by 6, that equals to 1 by 3. So mole fraction of component 1 or liquid 1 in this solution is 1 by 3, and mole fraction of component 2 in this solution is how much? 4 mole divided by 6 mole, that equals to 4 by 6, that equals to 2 by 3. Okay. So here you understand all the terms, what is P1, P2, X1, X2 and P total. Now the person comes Raoult. So this was the person who gave a relationship between vapor pressure and mole fraction of a liquid solution. Okay, Raoult was the first person to give a relationship between vapor pressure and mole fraction of a liquid solution. So what he told is, vapor in a binary solution of two volatile liquids, the vapor pressure of each component is directly proportional to mole fraction of that component in the solution. Okay, let me write this. Vapor pressure of each component is directly proportional to mole fraction of that component in solution. Okay, so now this is known as Raoult's law. So suppose for component 1, what will happen? Vapor pressure of each component, means vapor pressure of component 1, that I have told you as P1, is directly proportional to mole fraction of that component in solution, is directly proportional to x1. Actually I draw that figure, let me draw this actually. So this was the figure. Where liquid 1, vapor 1, vapor 2, and this is liquid 2. The pressure is P1, the pressure is P2. Okay, and the mole fraction of liquid 1 is x1 and mole fraction of liquid 2 is x2. Okay, so now see, for component 1 or for liquid 1, vapor pressure of component 1, that is P1, is directly proportional to mole fraction of that component in solution. Mole fraction of component 1 in solution, that is P1 directly proportional to x1. We can write it as P1 equals to P1 naught x1. So what is P1 naught? P1 naught is, what is P1 naught? P1 naught is partial vapor pressure of component 1 in pure state. Okay, vapor pressure, I am writing vapor pressure as Vp, vapor pressure of component 1 in pure state. Okay, what is P1? P1 is simply vapor pressure of component 1 in this vapor phase. Okay, but what is P1 naught? P1 naught is vapor pressure of component 1 in this vapor phase, but that is in pure state, means only component 1 is present. Okay, similarly for component or component 2, what will happen? P2 is directly proportional to x2. That implies that P2 equals to P2 naught x2. Okay, and what is P2 naught? Vapor pressure of component 2 in pure state. Okay, so P1 naught and P2 naught are vapor pressure of component 1 and 2 in pure state. Okay, so now see, this is P1 due to vapor 1 and this is for vapor 2, pressure is P2. Okay, so what is the total pressure? I have told it as P total. So if I write it, P total equals to, you guys know Dalton's law. According to Dalton's law, the total pressure of a solution is equal to partial pressure of each gas. Okay, so P total will be equal to P1 plus P2, where P1 is what? Vapor pressure due to component 1 and P2 is vapor pressure due to component 2, and when we mix these two we get the P total, that is the total vapor pressure. Okay, and what we have derived here? P1 equals to P1 naught x1, P1 naught x1 plus this is P2 naught x2. Suppose I am writing this like P1 naught x1 plus P2 naught 1 minus x1, because what happens guys, you know total mole fraction is always 1. If component 1, the amount of component 1 is x1, then obviously the mole fraction of component 2 it will be 1 minus x1, because the total mole fraction is always 1. Okay, now see here what we are observing from this relation. Here we can see that the total pressure is dependent on the partial vapor pressure of component 1 and 2 in pure state. Okay, and mole fraction of any one of the component. Okay, or I mean if you will write this like P1 naught 1 minus x2 plus P2 naught x2, then it is also right. Okay, these both are right. Okay, so total pressure depends on the partial vapor pressure of each component in pure state and mole fraction of any one component in the solution. Now let's draw a graph . Now let's draw a graph of P1 and P2 versus x1 and x2. Okay. Okay, here we see this is mole fraction of component 1. So when mole fraction of component 1 is 0 in the solution, the vapor pressure due to it will also equal to 0, because if there is no component 1, how a pressure will be created due to it? So when mole fraction of component 1 is 0, I have forgot naming it, let this is vapor pressure and this is mole fraction. Okay. So when mole fraction of component 1 is 0, the vapor pressure due to it is also 0. And when we increase the mole fraction of component 1 in the solution, vapor pressure will also increase, because that is according to Raoult's law, which says that vapor pressure increases if mole fraction increases. Okay. So here you can see when mole fraction of component 1 increases, its vapor pressure also increases. So this is the graph for component 1. Okay, and what happens when in the solution the mole fraction of component 1 is equals to 1? At that time, suppose the pressure is P1 naught. Why? Because I am saying that when mole fraction of component 1 is 1, that means only component 1 is present in that solution, and it indicates that component 1 is present in the solution. That means component 1 is present in its pure state, and when it is present in its pure state, the vapor pressure due to it is P1 naught. Okay, you can also see from here I have written P1 equals to P1 naught x1. So when mole fraction will be 1, P1 equals to P1 naught into 1, that implies that P1 equals to P1 naught. Okay, so when mole fraction of component 1 is 1, the vapor pressure due to it is P1 naught. Okay, and you see here when mole fraction of component 1 is 1, mole fraction of component 2 is 0, because component 1 is totally present. So obviously mole fraction of component 2 is 0. And you can see when mole fraction of component 2 is 0, the vapor pressure due to that component 2 is also 0. And when we increase the mole fraction of component 2 in the solution, its vapor pressure also increase. And at a point where mole fraction of component 2 is 1, or when mole fraction of component 1 is 0, at that time let's suppose the vapor pressure is P2 naught. Why? It is also the same thing, because I am saying that mole fraction of component 1 equals to 1 means the component 2 is present in its pure state. So obviously at pure state the vapor pressure due to component 2 will be P2 naught. Okay. Now what we will do, we join these points. Okay. We join these points. And what will be this? This will be the graph for P total. Okay. So here we can, this was the graph for component 1. So, and the pressure due to component 1 is P1 naught x1, and this is the graph for component 2, and the pressure due to it is P2 equals to P2 naught x2. Okay, and this is the curve for total pressure, that is equals to P1 plus P2, that equals to P1 naught x1 plus P2 naught x2. Okay, here you can see the total pressure lies between P1 naught and P2 naught. Okay, means the total pressure will always lie between P1 naught and P2 naught. And you can say that vapor pressure of total pressure, the total vapor pressure has a minimum value of P2 naught. Minimum value of total pressure is P2 naught, and maximum value of P total equals to P1 naught. What does this imply? It says that since due to as minimum value of pressure is P2 naught, means the component 2 is less volatile. Okay, so this component 2 is less volatile in the solution. As a result, the vapor pressure due to it is also less. Okay. Now we will see about mole fraction. Okay. Now we will see mole fraction of component 1 and 2 in vapor phase. Okay, remember it. Mole fraction of component 1 and 2 in vapor phase. I have already told you mole fraction of component 1 and 2, but that is not in vapor phase. I have told you in solution. Okay, I have told you in solution, but now we are going to discuss about mole fraction of component 1 and 2 in this vapor phase. Okay, so I have told x1 and x2 are the mole fraction of 1 and 2 in solution. Similarly, what happens in vapor phase? The mole fraction of component 1 and 2 are denoted by y1 and y2. Suppose add this y1 and y2, where y1 is mole fraction of component 1 at vapor phase and y2 is mole fraction of component 2 at vapor phase. You can see at this vapor phase, these are the vapors due to component 2 and these are the vapors due to component 1. So basically in vapor phase also these are present in different moles, and from that we are calculating the mole fraction. Okay, that is y1 and y2. Now if I write P1 equals to y1 into P1 naught, is it right guys? P1 equals to y1 into P1 naught? Yes. See this. What is P1? P1 is partial vapor pressure due to component 1 in vapor phase. What is y1? Mole fraction of component 1 in vapor phase. And what is P1 naught? Total pressure due to component 1 in its pure state. Okay, and this is true due to Dalton's law. According to him, partial pressure of a gas is equals to mole fraction of that gas into total pressure. Sorry, it is actually not P1 naught, it is P total. Okay, so this is P total. Similarly, what happens? P2 will be equals to Y2 into P total. Remember it, I am not writing x1 and x2, rather I am writing y1 and y2. Why? Because x1 and x2 are mole fraction of component 1 and 2 in solution, and y1 and y2 are mole fraction of component 1 and 2 in vapor phase. We are taking everything in vapor phase. P total is the total vapor pressure, P2 is the vapor pressure of component 2 in vapor phase. So that's why we are taking mole fraction of component 2 in vapor phase also. So we can write this x1. The right thing is we have to write it y1 here. Okay, so from these formulas we can find mole fraction of component 1 and 2 in vapor phase. Okay. So this was all about Raoult's law and liquid solution. Okay. Now students, let me tell you, this liquid plus liquid solution is of two types. Okay, again we are dividing it, and these are of two types. I am saying the first is ideal solution and the second one is non-ideal solution. Okay, so first let's discuss about ideal solution. Ideal solution. Okay students, tell me what is ideal solution? Okay, ideal solution is a solution that obeys Raoult's law over entire range of concentration. Means, and what? Okay. Now say me what Raoult's law? It says that vapor pressure is directly proportional to mole fraction, and I am saying that ideal solution obeys Raoult's law over entire range of concentration. Means there should not be any deviation from the vapor pressure when we change the mole fraction. Okay, that means we should get a linear plot. Okay, and that is known as ideal solution. Actually guys, it has two main properties. One is delta H mix equals to 0 and another is delta V mixture equals to 0. What is delta H mix equals to 0? It means enthalpy of mixture should be equals to 0, and it means that no heat should be absorbed or evolved when we mix two components to form a solution. No heat absorbed or evolve during making solution. And what is mixture of volume should be 0? That means the total volume should be equal to the summation of the volume of each component that we mix to form the solution. So these are the very important two properties for an ideal solution. Delta mix should be 0 and delta V mix should be equal to 0. Okay, and let me note this. Students, if we see at molecular level, then also ideal solution can be also described at molecular level. Okay, at molecular level. And before understanding this, let me draw some diagram. Okay, at molecular level, ideal solution can be described as if intermolecular interaction in every type is same as intermolecular interaction in AA type or BB type, then it is called an ideal solution. So let's understand this. Okay, you can see this is a liquid of pure component A. Okay, so what are present? So the molecules that are present here are the molecules of A. So obviously the bond will be between two A molecules. That's why we say that the intermolecular interaction in this liquid is of A type, means bond is between two A molecules, and obviously because this is a pure liquid of component A. Okay. And similarly, this is a pure component of liquid B. So the bond that is present is between two B molecules. So we can say that the intermolecular interaction over here is called BB type. And what happens when we mix these two solutions? When we mix these two liquids, we get a solution where, so this is a solution of liquid A and liquid B. So what happens here? Both the liquids A and B are present. Okay, so the bond can be between A and A molecule, B and B molecule, and also A and B molecule. Okay, so in this solution, the intermolecular interaction can be of AA types, BB types, or AB types. Okay. And I said that it will be an ideal solution, or a solution can be said as ideal solution if the intermolecular interaction of AB type is same as the A type or BB type. And while saying the intermolecular interaction, it means that the force of attraction. Okay, so if the force of attraction between one A molecule and B molecule is same as the force of attraction between two A molecules or two B molecules, if they are same, then it is called ideal solution. Okay, so we can write here that AB type, intermolecular interaction in AB type is same as A type or BB type. Okay, so that is called ideal solution. Let us take an example. Example is an hexane plus n heptane. What is n hexane? This is n hexane. You can fill the hydrogens. One, two, three, four, five, six. So this is n hexane, and similarly this is n heptane. Okay, this is n heptane. I'm writing the hydrogen here. So when we add n hexane and n heptane, we get a solution, and that solution is an example of ideal solution. And if I ask why, because you can see this n hexane and n heptane are of similar type. The only thing is here one carbon atom is more. Okay, so when we add this solution, mostly it has been seen that the molecular interaction in AA type or in BB type is same as the molecular interaction when we add these two liquids. Okay, so this was the example of ideal solution. Now students, let's talk about non-ideal solution. Okay, while seeing the ideal solution, what I told is that ideal solution obeys Raoult's law over entire range of concentration. So, for non-ideal solution, it is opposite, means it will not obey Raoult's law over entire range of concentration. Means there will be deviation in vapor pressure when we change the mole fraction. Okay. So, vapor pressure deviation is observed. Okay, in non-ideal solution, vapor pressure deviation is observed, and if vapor pressure is more than calculated vapor pressure, this is the observed vapor pressure. So if observed vapor pressure is greater than calculated vapor pressure, it is called positive deviation. And if observed vapor pressure is less than calculated vapor pressure, then it is called negative deviation. Okay, now let's understand what is positive deviation and how it is created. And we told that when observed vapor pressure will be more. So how vapor pressure can be more than the expected vapor pressure? Let's discuss it. Okay. If vapor pressure is more, positive deviation. Vapor pressure negative deviation. Okay, so when vapor pressure will be more, you see this is AB type interaction. Okay, and this is A type interaction or B type interaction. So see here, this is AB type interaction. If the bond, okay, if the bond is weaker in a AB type interaction, if this is weaker, then the AA type or BB type. If the intermolecular interaction in AB type is weaker than that of AA type or BB type, then we get higher vapor pressure. Why? Because if the bond between A and B molecule is weaker, what happens? This bond can be easily broken. Okay, and when this molecule and when these bonds are easily broken, what happens? When this bond is easily broken, this A molecule can easily go into the vapor state. Similarly, the B molecule is also can also easily go to its vapor state. Suppose to break this bond, we need 4 joule of work, and suppose for here we need 10 joule of work. So when we made this both type of liquids to form a solution, what will happen? this AB type, in this AB type, the bond will break first or at very low energy. So the molecules A is can easily go to vapor state. Okay, and what will happen when A or B molecule are easily going to the vapor state means there will be more vapor formed in the vapor phase, and if more vapor will be formed, then obviously vapor pressure is going to increase. So when the intermolecular interaction in AB type is weaker than that of AA type or BB type, then vapor pressure is more and we get a positive deviation. And to make you understand that deviation, let me draw a graph. So this is the y-axis where you have represented vapor pressure, and this is the x-axis where you have represented mole fraction. And we have already drawn this before. So here we can see that when mole fraction increases, vapor pressure also increases. So can you say me that whether it is a graph for ideal solution or non-ideal solution? Yes, it is a graph for ideal solution. We discussed previously ideal solution, and we said that there should not be any deviation in vapor pressure when we change the mole fraction. Means a linear plot should come, and here you can see a linear plot has come. So this is the ideal solution. And now I told about non-ideal solution and saying you about positive deviation. So what happens in positive deviation, the vapor pressure is more than the expected. So it will be something like this, and this. Okay, so these are the lines at black which indicates that it is the vapor pressure is good, and these are the blue lines which indicates that vapor pressure has been increased that we are calculating. So this is giving us a positive deviation because vapor pressure is increasing here. You can see it, vapor pressure is increasing here. Okay, and now let's discuss about the non-ideal solution, about negative deviation. So simply what happens if the intermolecular interaction in AB type is now stronger than the intermolecular interaction between AA type or BB type, means the intermolecular interaction or the intermolecular force of attraction between AA type or BB type is weaker now. So obviously, as an example, you can say we need 10 joule of work to break that bond, and we need 4 joule of work to break the bond. So when in solution phase, A and B molecules are present, it is saying that we need 10 joule of work now. So it is difficult to break the bond between A and B molecule. Okay, so what happens? It will be difficult for A and B molecule to go to the vapor phase as compared to that of AA and BB, because in that case, or in that pure component A and B, the A and B molecules can easily go to the vapor phase. But when you make the solution, we are making something like AB type where we need to require more amount of energy to evaporate it or to evaporate it. So obviously in this case it's difficult to go to vapor phase. So if molecules A and B are not going to vapor phase easily, then what will happen? Less amount of vapor will be formed here. And if less amount of vapor is formed here, what we see? We are getting a negative deviation. So that is negative deviation. So we talk. So this was the positive deviation. So what will happen in case of negative deviation? So what will happen in case of negative deviation? We will get vapor pressure lower than the expected vapor pressure. Okay, so these black lines are for ideal solution, and here you can see we are getting less vapor pressure as intermolecular interaction in every type is less, so we are getting less vapor pressure in this case, so we are getting a negative deviation. Okay, now let me give you some example. Positive deviation and negative deviation. Okay, we saw here attraction in AB type is weaker, and here interaction in AB type is strong. Okay, and if I give you example, so solution of C2H5OH plus acetone. Okay, and here example will be acetone plus chloroform. What is chloroform? Formula of chloroform CHCl3. Okay, so let's see here how attraction of AB is weaker here. Okay, so suppose we have C2H5OH, and what happens between two molecules of C2H5OH? The molecules of C2H5OH are bonded through hydrogen bonding. Okay, they are bonded through hydrogen bonding. Hydrogen bond is normally seen between two atoms if hydrogen atom is attached to whether oxygen, nitrogen or chlorine atom. Okay, so here you can see in ethanol molecule, this is ethanol, two ethanol molecules, we have hydrogen bonding. Okay, and when we enter acetone into it, what happens? Some of the hydrogen bonds are broken. Okay, some of the hydrogen bonds are broken. So what happens? Every time now when we add ethanol C2H5OH to CH3, C double bond of CH3, they also form hydrogen bond. Okay, let me write like this. They will also form hydrogen bond, but the hydrogen bonding here is more strong than this. Okay, so when we add C2H5OH and CH3COCH3, that is acetone, what is happening? The solution that we are getting, in that solution, the intermolecular interaction between them is weaker. Okay, and as it is weaker, the vapor pressure will be more, and we will see a positive deviation. Okay, and now talking about negative deviation, CH3COCH3 and CHCl3, chloroform and acetone. Okay, so see here, suppose at first acetone is present. Okay, can you say me which kind of bond is present? I mean, which kind of interaction is present in case of acetone? Actually, in case of acetone, since it is a polar molecule, it is a polar molecule. Since this is oxygen delta negative and carbon is delta positive, so this is a polar molecule. Okay, and between two polar molecules, the force of attraction is dipole-dipole interaction. Okay, so here dipole-dipole interaction is present. Hydrogen bonding is not present here because the hydrogen has been attached to carbon. Okay, so here dipole-dipole interaction is present. But what happens when we add chloroform to this? You can now see that when we add chloroform to this, C double bond O, CH3, it will form hydrogen bonding with chloroform. Why? Because these are the chlorine atoms which are so electronegative. Okay, so these are very electronegative. As a result, carbon is electropositive. As a result, what happens? We get a hydrogen bonding when these two molecules are added. So now here you can see that the intermolecular force of attraction between the acetal molecule and the chloroform molecule has increased. As a result, we get a less vapor pressure. Okay, as a result, we are getting less vapor pressure and hence we are getting negative deviation. So this was all about ideal solution and non-ideal solution. Okay, now after finishing this ideal and non-ideal solution, we finished all about liquid-liquid solution. What happens? We finished all about liquid-liquid solution. Now let's start solid plus liquid solution. Okay, so now let's start solid and liquid solution. So you guys tell me, you must have known that all solids are not dissolved in liquid. Actually that is rule. Okay, that is called polar dissolves in polar. That means polar solute dissolve in polar solvents and non-polar solutes dissolve in non-polar solvents. But here what we are going to focus is about vapor pressure of solid plus liquid solution. Okay, so to make you understand this thing, let me first draw something. Okay, okay, so I have taken two examples. In one container 50 ml of H2O is present and in another container 50 ml of H2O is there, but what we did that we add 2 gram of sugar to this. So this is a solution and this is a pure solvent. So students, can you tell me whether vapor pressure in this both container will be same or it will be different? The answer is it will be different. Why? Now question is why it will be different? The answer is, you can see in this pure solvent all the solvents are present over the surface of the liquid. Okay, so these are the solvent and these are the solvent particles that are present on the surface. So in a pure solvent only solvent particles are present on the surface, whereas in solution solvent molecules are present on the surface. That's fine, but what happens? Solute molecules also come to the surface, and what happens then? These solute molecules hinders the solvent molecules to go to the vapor phase. They will hinder the solvent molecules to go to the vapor phase. So what happens here? Less number of solvent particles will come to the vapor phase. Whereas in this case, since only solvent particles are there, more number of solvent particles will evaporate and hence more vapor will be created in the vapor phase. So since here more vapor is created, vapor pressure here in pure solvent is more, and whereas here less amount of vapor is created due to the hindrance of solute, here the vapor pressure is less. Okay, so what we observed from this example is that vapor pressure of solvent in solution is less than vapor pressure of pure solvent. Okay, so you should note about this, which says that vapor pressure of solvent in solution or that is called vapor pressure of solution is less than vapor pressure of pure solvent, and this is vapor pressure of pure solvent. Okay, so here vapor pressure is more and here vapor pressure is less. So what we concluded is that when we add a non-volatile solute to a pure solvent, the vapor pressure decreases.